Assalamu alaikum, my dear students. How are you? Hope fine. Last lecture, we have finished that when the work done when force acts in the direction of the displacement. You remember last time that I told you that work done is in fact equal to work done is equal to the work done was equal to what? F and to S. We came across this. Work measured in joule, which is equal to Newton meter. I told you work is done when energy is transferred from one form into another. Rather, it is the kind of measure of energy transfer. But I told you that there are three main conditions for the work done. One condition was that there must be force acting on the body, there must be force, there must be displacement, and most importantly, I told you that force and displacement are parallel. If they are parallel to each other, then work will be done. In this case, you see, look at this. There is the force acts in this direction, and the body is displaced from the point A, if you remember the previous lecture, to the point B in the direction of what? In the direction of force. Then we said that work is done, and that work was most probably 60 Newton. If you remember the previous lecture, 12 Newton into 5 meter, and that was 60 Newton meter, or you can say 60, sorry, what I wrote, 60 Newton meter or 60 joule. Then I finished my lecture that what if the force and displacement are not in the same direction, then will there be a work done or not? Then our today lecture, I will be explaining this part of the lecture to you. Look at the main. The main is pushing the cart in the direction is shown to you. Look, he is applying the force. The force which he applies is in this direction as you see. Look, this is the direction of the force. So the force is neither vertical, the force is neither vertical as you see, neither in this direction, and the force is neither in what? In this direction. Rather, the force makes some angle theta with the horizontal or with the ground. But if you look if you look to the displacement, you see the displacement is in this direction as you see. Look, the displacement is completely horizontal. Why? Because when he drag the box is not moving in the vertical direction. The box moves in the direction as I indicated, from A to B. Then this is the kind of situation where we need to calculate the work done, right? Because there is a displacement and there is a transfer of energy. But this is rather a bit complicated situation. Now, how we will calculate the work done? Let us see that in this situation, in order to calculate the work done, then we will use the idea of the resolution of forces. Resolution of forces. I think you have learned this in the previous chapter. clear the chapter number for the dynamics chapter. That look, although this force is not in the direction of what? It is not in the direction of displacement, but if you resolve this force into its rectangular component, which you have studied in the previous unit, you see, look, if I just resolve this force into its component, this force has definitely two components. You see, look, the component of the force, there are two component of the forces. One component which is along, look, the component of the force, this one, acting in the upward direction along the vertical axis. And you see, look, one is the component of the force that is horizontal. The horizontal component of the force. This component of the force is you see. One is this component of the force. Look. Now you have two component of the forces. The vertical component of the force, the vertical component of the force, this component of the force Fy. In the other, the horizontal component of the force Fx. So if you look into this diagram, in this diagram, it is what? That is, it is what? It is the horizontal component of the force component. It is the horizontal component Fx of the force which does work, right? This component of the force is doing work done, while the vertical component, the vertical component, the vertical component Fy does not do any work done. Why? The question is why this component does not do any work done. What is the reason? This component does not do any work done because of the fact that the reason is simple, is there is no motion. There is no motion of the box in the vertical direction. What does this mean? That S is equal to 0. There is no motion in the vertical direction. So the only component which does work is the only component which does work is the only component which does work is which one? Is the only component which does work is the horizontal component. This component of the force, it does work, right? So if I just revise my definition of work done again, is by the definition of the work done, what is work done? Work done is equal to what? F into S. Now you see that which component of the force is doing work done. The component of the force which is doing work done is now in fact not this F itself, which is the resultant. Rather, the component of the force is what? Fx into S, which does work, right? Now we know the force. We only know which thing. We only know this part of the force. We know this thing, right? This is known to us, but this is yet to be found. We don't know. But if you remember the resolution of the vector, you remember that this was our which component? If you remember, f and 2y. This was our which component? F and 2x component, fx component, right? This was by applying trigonometric principle, this fy was equal what? F sine theta. And this fx is equal to f cos theta. So what I'll write, that w is rather equal what? F cos theta into s, or I will write that w is equal to fs cos theta, fs cos theta, right? That is the formula for the work done when the force and displacement are not in the same direction. Rather, the force makes an angle theta with the horizontal axis, right? Look, why? Because if you draw the x-axis and the y-axis, look at this diagram as you see. This is our what? If I just draw this like the x-axis and the y-axis, then what is going to happen? This is our x-axis and this is our what? And this is our y-axis. So you see that the force makes an angle theta with the x-axis, with the horizontal, with the ground. So look, what is then this part of the equation? This part of the equation f cos theta, it is now what? It is, in fact, it is the component of the force. The component of the force which is in the direction of, which is in the direction of displacement, which is in the direction of the displacement. Now there are certain cases which I want to explain to you. Cases. In that cases, look, the case first one, case A. See here, f, this f theta is equal to what? If this theta is equal to 0 degree, then what will happen? That will be this situation as you see. Look in this situation. What is the angle between this displacement, this displacement S and this force? That angle between, that is the theta between them, is 0 degree. And what will happen? Look, the above equation will reduce to what? That, as we know that cos theta, that is cos of 0 is equal to 1. So what will happen? Then W will be equal to what? F into what? F into S into 1. And what does this means? Fs. In this case, this is the case of maximum work done. Case of what? Maximum work done. In this case, the work done is what? The work done is maximum. Now, if you remember, as I told you, that if someone is carrying a bucket of water along what? Along the horizontal direction, then I told you that does there be will any work done on the bucket of the water carrying plan? And the answer was what? The answer was no at that time. Why? Because of the reason that you see that look, F in this case, for example, it was like this case, and there was what? A man carrying a bucket of water like this, and the man was moving in this direction. This was the displacement. And look, what is the force? The force is acting in the downward direction. The force of gravity W, it was Fg. Okay, better to write that how much force is acting on the bucket in the downward direction, Fw, and that is mg. And then I told you that will the gravity does work on the bucket of the water. The answer is no. The answer is what? The answer is zero. There is no work done on the bucket of the water by gravity. Why? Because the bucket of water is not displacing in the direction of what? In the direction of the gravity. In order for the gravity to do work on the bucket, it must be what? It must be displaced in this direction, which it is not. So you see that the main is carrying the bucket in this direction, in the horizontal direction. So the gravity does zero work on it. Why? The work done by the gravity on this bucket. What is that? That log Fs into cos theta. So you see, you have the force, that is F gravity. You have displacement, but what is the angle? This angle between this force, this angle is 90 degree. So Fgs into cos of 90 degree. And if you use your calculator, you know that Fg into S into cos of 90 is 0. So what is the answer? The answer is 0, right? That no work is done. So whenever, what is the result? The result, I would like to write the result. The result is that whenever a force acts perpendicular to the direction of motion of the body, perpendicular to the direction of motion of the body, it the force does not do any work on it. Any work on it. There are many examples, right? For example, look, one interesting question I would like to explain to you. For example, if I ask you that will the centripetal force does work on the body, for example, let us consider a body of mass m. Look, this is body of mass m. The body is moving along a circular track, and let the radius is this one. This is the radius. The body is moving along a circular track, as you see every time like this, and you see this is radius, as you see. Look, and this is the will. This is the direction of the velocity. This is direction of the velocity here. Now look, you tell me that every time you see that your displacement is this one, for example, every time you just make this displacement, and look, what is the force? The centripetal force that acts, that is towards the center of the circle. For example, if you tie a ball or like as I did this with the string, and you are a stone with a string, and you whirl it around around a circular loop, then will there be any work done by the centripetal force? The answer is no. Why? Because you just see, for example, if I just consider your this segment of displacement, like this one, this segment of the displacement, for example, your displacement is this one, like this little bit displacement from this point to this point, as you see this displacement, and look, the centripetal force is this direction, and you see what is the angle? This angle is 90 degree. So what is the work done? The work done by the centripetal force, for example, what is the formula? Work done by your centripetal force Fc into S into cos theta. The work done by centripetal force. So Fc into S into cos of what? Cos of 90 degree. And of course, this Fc and S and this is 0. And what is the work done? So you see the centripetal force does not do any work done, right? So that is how whenever a force acts on a body, then if the force and the displacement are not in the same direction, then work done can be calculated by using this expression, like this one. As I told that this is what, now this is, as I told, that this is the component of the force which is perpendicular to displacement, right? Uh, Now let me show you some kind of uh, numerical which can help in understanding this numerical, this formula. For example, let us see there. Let me check some numerical regarding this formula. W is equal to Fs cos theta. Let me check. Where is, okay, let me construct my own. You see, for example, let us consider that, right, that the a student is pulling a school bag as shown in the direction. For example, he has a school bag like this. This is his school bag, right? He is applying a force on the school bag in this direction. He is pulling this along the track in the school, right? And he moves the school bag from, that is from the class, that is from the classroom, if this is the classroom, to the main gate, classroom and the main gate, and cover a distance of 200 meter. During pickup time, he moves the bag along the track from the classroom to the main gate and cover a distance of 200 meter. And he apply a force of, let's say, 70 Newton. He apply a force of how much? 70 Newton force he is applying while moving from the classroom, while moving the bag from the classroom towards the main gate. It is observed that the angle between the bag, the force he apply, and the horizontal track, that angle is 60 degree. Then calculate the work done by the student while moving, while moving the bag from classroom to the main gate. The distance covered 200 meter, right? And the angle at which the force acts the track is 60 degree. Then what will be the work done? Now, as we know that, look, you see, in this case, the force is not in the direction of what? In the direction of your displacement completely. So definitely we will be using which component of the force? The one which does work. And which component does work? Of course, the horizontal component of the force does work. And you already know that that horizontal component Fx is equal to what? F cos theta. We have just done this uh, minutes before. So you see what will be this work done, Fs cos theta. So your F is 70 Newton, your S is 200 meter, and the angle cos 60 degree. So 70 Newton into 200 meter into cos of 60. If you use your calculator, this will come out to be zero point 0.5 if my memory is sharp or helpful. So what is going to happen? This is 100, right? It will become 100 and 100 into 70. So that will came out to be 7,000 Newton meter, or you can say that this will be 7,000 joule, or you can say 7 kilojoule of work. So the students does 7 kilojoule of work while moving his school bag from classroom to the main gate 200 meters. So that is how we can calculate the work done when force and displacement are not in the same direction. So this is our today lecture. Inshallah, in the next lecture, we will start one of the most important topic, and that will be energy. We will be explaining energy in great detail. So let us wind up our today lecture. And the today lecture is that work done when a force and displacement do not have the same direction. When they do not have the same direction, then we will definitely look for the component of the force which is in the direction of the displacement. For this purpose, we will be using the concept or the idea of the resolution of forces. We will apply trigonometric principle, and we will find the component of the force that is in the direction of displacement, and it will be that component of the force which will does work. So that will equal Fs cos theta, and this is one of the most important equation, and it is applicable almost everywhere. Thank you very much.